Thank you, Chairman. This is a joint work with Professor Senda. In this work, we consider model-based Bayesian reinforcement learning. Reinforcement learning is a problem of exploration and exploitation. Roughly speaking, exploration means gathering information about uncertain environment, and exploitation means planning policy based on information. In model-based method, simulation samples are useful for reducing real-world samples. And if the model has only a few uncertain parameters, it can be estimated using a few real-world samples. In addition, in Bayesian approach, agents can use prior distribution of uncertain parameters, which is also helpful for reducing real-world samples. So, the advantage of model-based Bayesian reinforcement learning is the full use of prior knowledge for reducing real-world samples. This is an example penguin hole task which is performed in this work. The square means peg, the broken line means maximum likelihood hole, and solid line means real hole. The goal is to insert the peg into the real hole. In this task, equation motion is assumed as parametric model, but position error of real hole is uncertain parameter. In this situation, agent tries to estimate real hole and insert peg using a few real-world samples. Now, I quickly introduce MDP and BAMDP. MDP is specified by state, action, transition, model, and cost function. And the goal is optimizing cost to go objective function. Base adaptive MDP, namely BAMDP, is an extension of MDP. The extensions are considering uncertain parameter, parameterized transition model, and optimizing expectation of cost to go over prior distribution of parameter. Please note that BAMDP is a special case of POMDP. This is BAMCP, namely Bayes adaptive Monte Carlo planning, which is an existing tree search algorithm for discounted BAMDP problem. BAMCP performs trial and error in simulation and uses the planned policy in the real world. The key ideas here are UCT, model parameter sampling at root node, and rollout for leaf cost estimation. The last idea depends on the fact that for any rollout policy and gamma less than 1, cost to go after t equal d is less than this equation. So it tends to 0 as d increases. One challenge in model-based Bayesian reinforcement learning is the computational efforts. And BAMCP finds a solution to discounted BAMDP problem. But how to find a solution to stochastic shortest path BAMDP problem, which considers undiscounted cost to go, this is the motivation of this work. Now I quickly introduce stochastic shortest path MDP. SSP additionally considers cost-free termination state and optimizing undiscounted cost to go. Please note that SSP MDP is more general setting than discounted MDP. And agents need to use a proper policy. A proper policy is a technical term in SSP. A proper policy means bounded cost to go equal to task achievability. If agent does not use a proper policy, cost to go diverges. Now, I'd like to talk about our approach. So we firstly want to solve the BAM-DP extension of SSP problem, but this is very difficult. So we approximate the original SSP BAM-DP problem by finite horizon BAM-DP problem described here, and leaf cost estimation problem described in this part. This part is the same as BAM-CP, and this part, each leaf cost is approximated by cost to go of proper stationary policy chosen for the leaf belief state instead of rollout simulation. So in this approximation, why do we choose policy at leaf? In discounted problem, for any rollout policy, cost to go after T equal D is less than this equation. So leaf cost is finally approximated by 0 as D increases. This is independent of the choice of rollout policy. On the other hand, in SSP problem, leaf cost is not finally approximated by 0. It depends on the choice of policy, so we want to choose the policy. The next question is how to approximately solve this approximate problem. Our approach is combining Monte Carlo research, robust reinforcement learning, and Bayesian inference. Firstly, Monte Carlo research considers a policy for finite horizon BAM-DP problem. We performed model parameter sampling and UCT simulation. This is same as BAM-CP, and we modify leaf cost in MCTS in the later slides. Secondly, robust reinforcement learning considers the policy for leaf cost. Proper stationary policy for multiple MDPs is a kind of robust policy. We performed model parameter sampling and reinforcement learning simulation. This idea is seen in many previous works. And we construct a finite set of proper stationary policy. Choosing a policy improves the leaf cost, as mentioned before. In practice, we can only use a limited number of policies. In this work, we manually construct a set, but how to construct effective set is future work. And thirdly, Bayesian inference considers the leaf belief approximation described here. BAM-CP does not need leaf belief because it uses only one rollout policy. But to tackle SSP problem, we need leaf belief for choosing a policy. We approximate it reusing previous MCTS simulation samples. To summarize, leaf cost in MCTS is given by the following step. Leaf belief is approximated by Bayesian inference. Best stationary policy for leaf belief state is chosen from a set of proper stationary policy learned by robust reinforcement learning. And finally, leaf cost is estimated by cost to go of best proper stationary policy for the leaf. I quickly show my results. Equation of motion is parametric model which agent knows, and position of real hole is uncertain parameter which agent does not know. We implement our algorithm with the following simplification. That is, grid-based function approximation for cost to go and Bayesian inference, and considering 6 discretized actions. For more details, see our paper. This slide shows a policy for maximum likelihood fall. Agent tries to insert the peg straightforwardly because it does not consider the error. Due to the position error of real hole, it easily fails. This slide shows the policy learned by robust reinforcement learning. Agents keep using one robust policy. It is improved, but it is not enough. This slide shows policy by our approach. Please look at here. If agent observes the contact at t equals 3, agent chooses different policy. In this boundary P, agent successfully achieved the task. This is a summary of this work. Firstly, a model-based Bayesian reinforcement learning fully uses prior knowledge for reducing real-world samples. We approximated the original SSP boundary P problem by this approximation problem. And to find an approximate solution, we combine the idea of robust reinforcement learning, multi-route research, and Bayesian inference. The features work are experimental evaluation for other tasks, implementation with advanced approximation, such as neural networks, and effective set of stationary policies for leaf cost estimation. Thank you for your attention.
Questions?
All right. So thank you for the talk. I was wondering, so you are kind of trying to use these robust policies that you've learned with a robust learning algorithm, you said. And so this is done then in advance, or how does that work? Because the idea here is to reduce sample complexity, right? But there now seems to be a, well, offline or preliminary first learning problem that you need to solve.
We run in simulation. We construct the set of robust policy in simulation offline, and in simulation run the MCTS. This is also offline, and apply the policy in the world. So this is.
I see. So the robust learning all uses simulation, which makes use of the uncertainty you have in advance, and you don't need any real-world samples yet. Is that right?
Can you repeat?
So you don't need any real-world samples yet in order to construct these robust policies. That's the idea, right? You know, that makes sense.
Yeah, but only using robust policy, it does not achieve the task because uncertainty is very large. So to adapt the uncertainty online, we developed this kind of approach.
Okay, so I guess then, if I can ask one follow-up question, then the logical question would be, so what will happen if you would retrain the robust policy after you've obtained more real-world data?
This is just my future work. Online relearning is future work. So
okay, well, that's fair enough. All right. Thanks.
Okay. Thank you.